Okay, now let's state and prove our first theorem of chapter 1. I didn't quite complete the theorem up here. Let's see if we can figure out what's missing. If AN converges to A, and AN converges to B as well, then you might be able to guess what that means. A is equal to B. It is impossible for a convergent sequence to converge to two different real numbers. Okay, let's do this proof by contradiction. So remember what we have here. If this is true, this left-hand side, then the right-hand side is true. In other words, the left-hand side implies the right-hand side. So what we're going to do is assume the right-hand side, the conclusion is false, and we'll prove then that the left hand is false. That's a proof by contrapositive. It's a form of proof by contradiction, and we need to get used to these proofs. All right, I'll make a note that it's by contradiction. And if we're specifically proving that this false implies this false, then that you could say it's a proof by contrapositive. We'll see when we finish the proof if we did that. All right, well, let's suppose that they are not equal to each other. Suppose A is different from B, and we will assume that A is less than B. Sometimes I'll make a note that if we chose B to be less than A, the proof is similar. In fact, it's nearly identical. You just switch the letters. So you don't have to prove it both ways. So we will assume that A is less than B. All right, so that means B is bigger. What I'm going to do is I'm going to let epsilon equal B minus A over 2. That happens to be the half of the distance between A and B. Since AN converges to A, there's a capital N in the natural numbers, such that if little n is bigger than that capital N, that implies the distance between AN and its limit is less than epsilon. And I'm going to write it in a different way. I'm going to write AN is in between A plus epsilon and A minus epsilon. Means the same thing as using the absolute values, or AN is in the interval A minus epsilon to A plus epsilon. Another way of writing it. They're equivalent. Now notice that A plus epsilon, remember that A is the smaller of the two numbers. And we defined epsilon to be the half of the distance between A and B. So this is equal to A plus which if we do some algebra, we can see that this is actually equal to B minus A over 2. Which of course that makes sense. This is epsilon right here. A plus epsilon is going to be the same as B minus epsilon, because epsilon is half the distance between the two. I'll let you work out the algebra there. It's just one baby step, I think. And this is equal to B minus epsilon. So the point of that was showing that A plus epsilon is equal to B minus epsilon. In particular, there are infinitely many points. In particular, there are infinitely many points or real numbers or terms of the sequence outside of b minus epsilon to b plus epsilon. By the lemma that we just talked about earlier, what did I call that? Lemma asterisk, I believe, in the previous video. AN does not converge to B. And that is a contradiction because AN converges to B. So this actually is a proof by contrapositive. We showed that if this is false, then this is false. The part that says AN converges to A and it converges to B, we just showed it doesn't converge to B. So the left-hand side is false. And let's see if I have, let me draw a little picture. This will say we're graphing the height, the horizontal line at height. Let's see, we chose B to be bigger than A. So this is B and A. And we got a bunch of terms of the sequence, and we're claiming that it converges to both of these numbers. I mean, so we're assuming that it converges to A and B. That's where we are going to reach our contradiction. So we chose epsilon in a way so that our little epsilon tube around B, that's B plus epsilon, that's B minus epsilon, which is also equal to A plus epsilon, and then this one would be A minus epsilon. All right, well, since it converges to A, from some point forward, from some capital N on, all of the terms of the sequence are in this tube because it converges to A, which means there is nothing in this tube around B. And remember, it requires that, by the lemma earlier, there are infinitely many terms outside of this tube because they're in this tube. And therefore, that sequence cannot converge to B. That's the end of the proof.